special pleasure for me to announce my Doktervater and one of my Dokterbrüder as this next speakers on the empirical significance of symmetries.
Dear Guido, thank you very much. And indeed it is an enormous pleasure to be here. Indeed it's an honour as well as a pleasure. And I know Henrique joins me in this. It's a great honour and privilege to be able to celebrate Professor Tov's 20th anniversary of this Nobel Prize. And indeed, as many people have remarked, it's an honour and a privilege not just for reasons of intellect, but also for reasons of personality. It couldn't have a happier as well as more creative intellectual atmosphere as we are here today.
Also, the microphone on?
Oh, crucial. The microphone is not on. Excuse me.
No, I guess. It is on.
So, I hope you heard all that. Anyway, it was nice, but now we'll get down to the nitty-gritty. So, in this talk, I will begin and Henrique will do all the heavy lifting in the last two-thirds. We are concerned with the empirical significance of symmetries. The fact is, of course, that symmetries obviously have considerable empirical significance, but we are especially concerned with a recent philosophical debate about what is called their direct empirical significance. And in this debate, the main technology that we want to advocate is a framework developed by Henrique together with Riello and to a lesser extent Florian Hopfmuller, in which one has a connection form on the field space of the gauge theories. Everything that we say will be in the classical setup, and I will talk about the philosophical generalities, and then Henrique will expound the elements of the application of this framework. So here in one slide is the overarching message. Everybody agrees that if you have a symmetry applied to a part of the universe, and the paradigm example is a velocity boost of Galileo's ship, then such a symmetry has a direct empirical significance in the sense that you can observe that processes in the cabin unfold in the same way whether or not the ship is moving relative to the shore. So there is a symmetry, a sameness, but there is the direct significance that the relationship to the shore is different in two cases. It's moving or it is at rest relative to the shore. And so you have empirical access to that relationship. Is it moving or is it not? And that is the empirical, observable witness to the symmetry. And our question is, and it's one already in the literature, can the gauge symmetries have a similar significance, which is in some way witnessed by an analogue of Galileo's ship? And since gauge has a strong connotation of redescribing the physical state in different words, whereas the ship really is boosted and there is a different relative velocity before and after the shift, the boost, because of that contrast, the traditional answer is that gauge symmetries would not have such a witness. But Greaves and Wallace argued that they do, and we're going to endorse that in a qualified way. So the traditional view is in fact articulated by Harvey Brown and Catherine Grading, and indeed part of the reason that Henrique and I decided to talk about this was that there is, from 1980 Scientific American, an amazing article by Professor Tovt on the gauge theory of elementary particles. And if I may say so, I hope there's no editor of Scientific American here today. Those were the great days of Scientific American. It's It's a wonderful article in which a beam splitter is discussed, and the closed beam splitter is, in fact, in this literature, in, for example, Grading and Brown. But the Greaves-Wallace paper disagrees with this traditional view, and the other two references by Henrique and co-authors are two of the several things in which this framework has been developed. So there'll be 5 sections altogether, and the first section is short, and then I'll talk about gauge symmetries having direct empirical significance. But the philosophical preamble about symmetries is just to remind people of some philosophy literature, in addition to this debate itself. So this is a notation we will use somewhat. A symmetry will be a little a for automorphism. There'll be a state little s in a state space curly s. There'll be a quantity q in a space of quantities curly q. And a symmetry, little a, is a map on states which sends a state to another state which has the same value, not for all quantities, but for all the quantities in some large set of quantities that is relevant to the situation at hand. And agreed, slight side comment, one can instead say that a symmetry is a map on quantities, and one also must sometimes consider not equality of values, but a kind of covariance of values. But for us, the main topic is the notion of gauge as descriptive redundancy prompts the question, does a state and its symmetry transform always represent the same physical state of affairs? And so mathematical state versus physical state is one jargon. Here, physical state of affairs has the same rough meaning as physical state. It's not philosophy jargon for something else. It just means physical state or state of the world independent of description. Now, I think the obvious answer to this italic question is certainly not always on usual definitions of symmetry, but under what conditions is the answer yes? When are little s and its transform a of s physically equivalent? When do they represent the same physical state?
Can I just ask a little question, not get totally lost? Your ship moving with respect to the coast, of course you can see that. But the Galileo transformation transforms both, and you can't see it.
Yes.
So what is now, what road should I follow? And the Galileo transformation definitely transforms both. You know, your ship,
yes,
that's like a rotation. Of course, if you have
yes,
one direction fixed and you rotate another one with respect to it, you can of course see it. But a complete rotation symmetry will rotate both. So
yes. This
what
is.
should I understand now?
Well, this is completely, I think, treated by the next slide or two. But you're absolutely right. There is a tradition that when you make the transformation of all the material contents of the universe, and therefore you certainly cannot see it in your words, then one should say that they represent the same physical state of affairs. That is what you might call a Leibnizian tradition, as against a Newton and Clarke tradition. This will be unfold in the next few slides, I think it's fair to say. So, here we go. I mean, counting possibilities is a favourite topic for philosophers, since, for example, the Leibniz-Clarke debate. And so this question at the bottom of the first slide, when are S and AS equivalent physically, it really relates to 3 debates, and we will be concentrating on one. But there are 2 other closely related debates. One of them is, in fact, exactly triggered by what Professor Henrique just asked. Many want to join Leibniz in saying that S and A of S are physically equivalent when S is a state of the whole universe. And this is to say that a symmetry transform of a state of the whole universe must represent the same physical state of affairs. And I think in the philosophy community, this is often considered a kind of Oxford doctrine. we tend to, this slide deliberately honours, we're both Cambridge men, Henrique and I, this deliberately honours the Oxford School of the Philosophy of Physics by only citing Oxford people, though I'm happy to say that here in Utrecht, a representative of that tradition, Niels Martens, has himself joined the forces of goodness that are listed here. So Reed and Müller-Nielsen in Oxford endorsed caution concerning that. Are they always physically equivalent if it's the state of the universe that's at issue? And a closely related question, this is the other debate, is, well, if you have a theory whose solution space is partitioned by a group of symmetries, setting aside the topic of interpretation of the theory's models or solutions as they stand, what about the idea of quotienting the theory? On this topic, there's an A and a B, an option. Should we, in fact, write down a quotiented reduced theory? Or should we resist quotienting and take the symmetry-related solutions to be isomorphic? And again, Dew and Colton have emphasized that reduction is not to be taken lightly, and this will be a theme in Henrique's second half. Okay, our own main debate, though, is adjacent but different from those two, which are even more closely related. It's this question of direct empirical significance, or being able to see it, as Professor Bertrand just said. And of course, all agree that symmetries have many important empirical implications, as I said at the beginning. The obvious examples come from the Noether theorems. And all agree that some symmetries, if you apply them to a part of the universe, do have the direct empirical significance that, as we said, you can see it, Galileo's ship. The relative distance between the ship and the shore changes. That's called by Grading and Brown in the literature a kind of transformation condition. There has been a transformation, but the processes in the cabin unfold in the same way, whether or not the ship is moving relative to the shore, which Grading and Brown call a symmetry condition. So there really is a symmetry, a dynamical symmetry. And I apologize to Carlo and Guido for having this in English rather than in Latin or Italian. However, even in English, it is well, thank you, Italian, right? What do I know? I'm English, so I only speak one language, as Damon was joking yesterday morning. In any case, even in English, one just has to smile and enjoy the glory of this prose. Have with you some flies, butterflies, and other small flying animals. The fish swim indifferently in all directions. The drops fall into the vessel beneath, and so on. Okay, so I commend to you the style, as well as the content. And so our question is, can gauge symmetries have a direct empirical significance? Traditional answer is no. Greaves and Wallace say yes. We wish to say yes in a qualified way. So the general question is, the general situation is, can there be two physical states, one for each of two regions, the ship and the shore, that are related or glued together in different ways? Or to put the same question in terms of states of the universe, let me call them universal states, and in terms of subsystems rather than regions, little Roman 1, there really are two universal states that are physically different. That's like, I only boosted the ship. Right? There are two universal states, S1 and S2, that are physically different. They're not related by a universal symmetry. But the universe is composed of two subsystems, the ship and the shore, or if you prefer, the ship and the sea. And for each of them, the physical state in S1 is identical to its state in S2. And therefore the difference between the two universal states lies in the relations or in the gluings, in Professor Electric's gesture, in the angle, right? So this is straightforward for Galileo's ship. Within the ship you cannot ascertain its position and velocity relative to the sea or the shore. And the variety in the relationship, the variety in the gluing is given by translations and boosts. and we are going to use the framework of the connection form to urge the same about gauge symmetries. There is, in fact, a finite dimensional parameterization of what you might call rigid, because not space-time variable in their action, rigid symmetries, a finite dimensional parameterization of that variety of gluing in a gauge theory. Okay, so, I'm sorry, I'm a little bit repetitive here. If gauge transformation is just a redescription, it is very natural to adopt the traditional view. How can one possibly change or induce a change in a physical relationship or gluing by a redescription of one region of the universe? Right? It seems there's alpha and there's beta. I'm going to redescribe alpha without actually changing it. I merely redescribe it. How could that change the relationship between alpha and beta? I only moved from Latin to Italian or something in my description of alpha. But we are going to argue that in a gauge theory there can be two universal states whose physical difference corresponds to a gauge transformation. And this physical transformation of the universe, when restricted to the subsystems, doesn't change their physical state. It's pure gauge. And we have settled on calling such a gauge transformation of a subsystem that does not extend to a universal gauge transformation parochial. Because parochial connotes, in English at least, I think also in the USA, not connecting to the wider world. It even got a negative connotation of being narrow-minded. And it's this parochial gauge transformation that has the direct empirical significance. Such a transformation is not identity at the boundary. If it were identity at the boundary, it could be extended as identity beyond the boundary, and then it would indeed not be parochial. Because it would be a universal gauge transformation. So what's happening here is a bit confusing, and we want to urge jargon which reflects the fact that two distinctions are independent of one another. So there are two distinctions which, when I state them, it's obviously true that they're independent. They cut across one another. These are the four words, and then there's also the word parochial, which is, in a way, the central word for us. But the idea of the parochial transformation has its place clarified by using this jargon. The Greaves Wallace, the literature in general, keeps talking about local versus global. Those words are natural for two different distinctions, but the two distinctions cut across one another. So we would like to abandon both local and global and use four different words. Okay. So first of all, little Roman 1 is a transformation applying to all of the world or less than the whole world. Universal versus regional. Second topic, does a transformation vary perhaps smoothly in its action at each space or space-time point? Is it in that way specified in a variable way across space or space-time? If so, often called local, but we'll call it malleable. Malleable English for bendable. If not, if specified by a finite number of parameters, often called global, but we would like to call it, please, rigid, which does occur in the literature, of course. I think malleable is Henrique's innovation. Being not English, of course, Henrique speaks several languages, as you will discover. Okay. So, I mean, now this is again a bit repetitive, I'm spelling it out. Both the universal and the regional could depend on an infinite or a finite number. Both the malleable and the rigid can be either regional or universal. The two distinctions cut across. So there are four cases. And our central question is, can there be two pairs of smoothly joined regional configurations where the second pair is differing from the first only by what we call a parochial symmetry, which is regional? and that means a symmetry of one region which does not extend to a symmetry of the whole. And this transformation isn't a symmetry, but it leaves the two subregions individually unchanged, so the only thing it can change, just like the Galileo ship, is the relation. So, traditional answer no, Greaves-Wallace yes, and we're going to agree with Greaves-Wallace, but our main claim is that these direct empirically significant symmetries are parochial, yes, obviously, by definition, but they're rigid. So they're parochial and regional, that's inevitably part of our dialectic given our jargon, but they're rigid. And Greaves and Wallace take them to be malleable. And this is a corollary of a gluing theorem that comes from this framework of Henrique and Riello and Hopfmuller. So, to summarize, there is a kind of regional rigid symmetries worth of states that are regionally gauge equivalent but have a relational physical distinctness. Now, at this point, as Fermat nearly said, the space-time region of my talk is too small to contain the justification of all these assertions. But fortunately, I have an intellectual policeman who has gone beyond my Fermatian margin and will now justify everything I have claimed.
Thank you, Jeremy, for that very nice introduction. So I'll jump right into it so we don't lose much time. And yeah, I echo Jeremy's nice words about the organizers and for inviting us. So, right, so as I said, I'm going to jump right into it. So first of all, we need to think about subsystems in the context of gauge theories and field theory, albeit classical, in terms of regions, right? And essentially what we want to know is, given some regional physical content, will there be any freedom left in how we glue different regions together to form a universal system? And this is the freedom that will give rise to direct empirical symmetry that Jeremy was mentioning. Immediately, we face a question that has kind of resurged in the literature lately when discussing entanglement entropy for black holes and things like that. That talk about subsystems and regions in gauge theory is a bit complicated. And this is because physical degrees of freedom of local gauge theories are to some extent non-local, right, through, let's say, the Gauss law and so on. And you can also think of it in terms of Wilson loops. If you have two regions, or let's say R and a complement of R bar, and you have holonomies that are not contained in one of the regions, then the observable related to that will be neither an R or an R bar. So the question is, what is the relation between the gauge invariant functions, and this is, of course, schematic so far. What is the relationship between the gauge invariant functions of the union of the two regions and the two regions individually? Sorry. So let's talk about regional information in gauge theory. To parametrize the gauge invariant functions wherever, we usually employ gauge fixing, right? Parametrize uniquely. And so if we try to attack the question of how to compose gauge fixed regional information, we can now write down something more specific. I will use this notation of sigma minus and sigma plus, and the boundary between them is S. It is useful to use this notation plus and minus just because you can unify notation sigma plus minus when you mean something that is valid for either region. And I use this notation here. So in gauge fixed speak, suppose we have two regional transverse gauge photons which don't match at the boundary. So I have a bar here, which means it's gauge fixed. A plus minus, I have the transverse, but they don't match at the boundary, right? And you're given these two unique descriptions of the physical states and they don't match at the boundary. Then the question is, can we still glue them to make a universal transverse photon A bar, now without the plus minus? And so in the next couple of slides I'm going to give some illustrations of what are the obstructions to that. So I think the easiest example is an analogy which I termed the dictionary extinction event. And there are two regions. This one only speaks Brazilian Portuguese, which is my language, and the other is German. And this is me trying to cope with the World Cup, trying to work through my trauma. And so, and suppose now that, you know, in each region there's the language edict that says you can only speak Brazilian Portuguese. You will no longer speak any other language, and no other language is allowed. There's no need for other languages, and all dictionaries are burned. And now the two regions, and the same thing happens in the German region, and now if the two regions meet, they can't communicate, right? And the analogy here is that language edicts are kind of gauge fixing, and dictionaries to go between the languages are the gauge transformations. Of course, if there was a single global region in the world, there would be no problem with that. You could burn, you could restrict to a single language, and no one would notice in describing everything. We all know what we mean by Popodar. We all mean the same thing. And this is, so now there's also an illustration due to Carlo, this is more about gauge invariant data. This is a nice paper in, I think, 2013 called Wide Gauge. I'll cite it in the bottom of the page. And Carlo's argument is that we need to retain gauge variant variables, variant, not invariant variables, to couple subsystems. So the idea here is, suppose there's a fleet of ships, and you have some Lagrangian, and the Lagrangian is expressed as a difference in velocities, and therefore is a difference in velocities, and the position variables are expressed in terms of some origin. And of course there's a symmetry here, in which I translate the origin. But I could go to frame invariant variables, which I call Q bar, in this, and just forget about that information that was floating around. And that's fine. I could describe this subsystem. But then suppose I have another subsystem, another fleet, and I do the same thing for that. Now I won't be able to, if there are interaction terms between the two ships, that I might not be able to describe the whole global system, universal system. And for that, you should retain some gauge variant variables so that you can couple the two systems together when they come into contact. And I think Carlo called this a gauge as a handle for coupling subsystems. And the issue is that gauge fixing and reduction are too inflexible. So here is a picture of field space. I won't talk more about this, but this is just a first illustration of it. And here I have two different field configurations, A and B prime. And there, when I talk about a gauge fixed system, I only talk about things in this surface. I don't move around. There is no way of me to moving around. I restrict my information here. In terms of, well, and so you can imagine that I have, or if I reduce, then I try to describe my system directly in the base space, which is a quotient, right? Because I'm quotienting by all the gauge symmetries. And then, and again, this is fine if you have knowledge of the whole universe, but as soon as you have two subsystems coming together, it's not clear how you can couple these quotients or these gauge fixed surfaces, because you have lost information about the embedding. Right, so maybe the simplest solution is not to gauge fix, not to reduce, but to decompose. And what do I mean by that is, well, suppose you can decompose processes into something that is a pure gauge part, in a way, and a physical part, but you'd retain the pure gauge part. This echoes the standard Helmholtz decomposition. So, to remind you what that is, suppose I have differential forms, which here I'll call lambda and lambda perp, for reasons to become clear soon. Suppose these are n differential forms, kappa is one less degree. Then I can always decompose, so here I'm imagining the manifold is topologically simple. And here I'm decomposing my differential form into something that is exact and something that is, in a field space sense, perpendicular to that part, which is exact. What do I mean? So the definition of this lambda perp is the unique one such that the adjoint of the exterior derivative is applied to it as 0. So this condition comes from an orthogonality condition, where I just illustrated for one forms, because it's simpler, you could formulate it for n forms, just using the Hodge star. It might be easier, but this I think is more pedestrian. And here you see the inner product that I'm using is an inner product in field space, in the sense I'm integrating the values of lambda all over the underlying manifold. This is the definition of the adjoint. And this is what essentially what Helmholtz does. It gives you a decomposition of something, and in the case where lambda, where n equals 1 of one forms, I will have this exact term is just a gauge transformation, d kappa. And the interesting thing about this approach is that now you can apply it to non-abelian fields as well. You can try to. So what I'm doing here is I'm describing to you how I'm going to decompose these processes or states and so on, or the gauge information about my system. And then I'm going to tell you how this decomposition helps me when I want to glue subsystems. So, but first, what I'm going through now is telling you how does one talk about this decomposition into, let's say, something that is the handle and something that is the physical information about the system. So the first step is you extend Helmholtz to non-abelian fields. And so here I will introduce a little bit of notation, but it should be familiar to most people. If I have a Lie group, G, I have the group of gauge transformations, which I'll call this curly G. So there's a choice of the Lie group element per point of the underlying manifold. This is the infinitesimal gauge transformations. So it's just mapped into the Lie algebra of G in the same way. Usually people call the field space for A this curly A, but I think in verbally it becomes a bit awkward because I'm going to be, there's a redundancy of saying A all the time. So I'll just call it 5 for field space. Right, so here A mu is one form, this is a base of one forms, a base of the Lie algebra. Everyone has seen this. This is the transformation, the infinitesimal transformation. I will call this big D here. It has some dependence on the base point, A, right? Because it includes this commutator of the Lie group, of the Lie algebra of the group. And so now you notice that if you want to talk about exact terms, instead of just being usually the exact terms d kappa, it will be covariantly exact, right? It will have this big D which contains A implicitly. So the pure gauge terms now are A dependent. In the field space parlance, it will be base point dependent. Base point, I mean, dependent on the point in field space that you're analyzing. We'll go through this shortly. And so the other thing that you want to add to the standard Helmholtz decomposition is a discussion of boundaries and regions, which is usually, well, not there in the context of non-abelian fields and so on, and how to glue it. So let's get into it. And so now I'm going to tell you, this is where the connection form comes in. This is, it formalizes this whole idea. And then in the last section, I will tell you how it's used to glue processes and how it gives you the actual, how it informs you what the directly empirically significant symmetries are. Right. So this is a field space, and I'm looking at it as a principal fiber bundle. So usually you have my field configuration variable here is a choice per point of the underlying manifold, and I can gauge transform it. It takes me to a different section of a manifold. But in the field space picture, each entire configuration of the universe of the underlying manifold is, of course, corresponds to a single point, right? This is an infinite dimensional manifold because if I change the field over here, it will go to a different point, and then there's an infinite number of ways I can change my field in different places. And this bracket denotes the equivalence class, the quotient. This is the orbit of that. And this psi hash is a usual notation if you look at it in the geometric textbooks. It's a way to relate the gauge transformation, so to the respective infinitesimal transformation of the field itself. So one thing is the abstract gauge transformation. The other thing is how it acts on the fields. And how it acts on the, so something happens here, so this would be psi, and then psi hash is something that moves your field configurations up and down this orbit. Here it's infinitesimally. So psi hash is an element of the tangent space to the field space at this point. Its components, this is very much similar, it's analogous to the finite dimensional representation where you have, let's say, dx for a basis of the vector fields, but this is all infinite dimensional now. So it's still represented in a basis where this is just saying that this is a vertical element, it's a pure gauge transformation element. All right, so this is a lot to digest. Let's go to a simpler picture. Usually, what I have described, I said, look, all the configurations along a fiber are physically equivalent. They're related by gauge transformations. So, if I want to observe physical change, I have to move from fiber to fiber, right? There has to be some horizontal component of any change for it to be physical. So if you think of a curve in base space, that it goes from physically distinct configurations from one to the other, then you can lift this, and the lift will necessarily have some horizontal components. Horizontal meaning that it doesn't just go along the fibers. Right. And since we're talking about field space, it's just useful to have a separate notation for things that happen in field space. And the easiest way to do that is just to adopt all the notation from space-time and double struct it, and that means that it's now the same type of operator operating analogously in field space. So for example, this double struct D is the field space exterior derivative. If you're acting just in functions, this would be just a derivative, or the functional derivative delta, but you can generalize it to act on one forms in field space. And so on. So this is the field space vector field, this is the Lie derivative, and a product. So, right. So what is the connection form in field space? The connection form in field space is a very simple object. It just takes whatever change you have given it, whatever infinitesimal process you give it as input, and it tells you what is its. So I give you any vector here, and you don't know how much of that is a pure gauge change and how much of that is a physical change. And the gauge connection, the field space gauge connection tells you, well, a part of it is pure vertical, it's pure transformation of your frame in a way, and a part of it you can count as physical. It maps uniquely to horizontal vectors. There are a couple of conditions that you need to satisfy for this to be a connection. in field space, and these are again analogous to the finite dimensional case. So a connection form, first of all, just very quickly, a connection form is a Lie algebra valued one form on your space. And in this case, it's valued on the group Lie algebra of the gauge transformations, right? So infinitesimal group transformations. Right. And given any x, I will give you a unique vertical horizontal decomposition. You might ask, well, if you give me a gauge fixing, is there an analogous connection related to that gauge fixing? And essentially, yes. There's a basic difference is that a gauge fixing usually will be restricted to a surface like this, but a gauge connection as a decomposition, and by the covariance property, it foliates your field space in a different way. So you can ask me, what if I gave you a process here, but I gave you a process in a different representation, and so on. And I can talk about all of them. And this is what will allow me to do, is because I have this flexibility. And in fact, so usually for abelian fields, the connections that we will look at are flat, so there's no curvature of this connection here. But for non-abelian, we have non-flat connections. And this is the more general case. There are non-flat connections in field space. By the way, this is how you also avoid the grip of ambiguity and so on, but I'm not going to get into that. Now we can introduce the generalized normals. It's this var pi coming from an inner product in field space. There is a natural inner product. I won't discuss it very much. You can look at our papers for our defense of it. And then you can call the vertical space just the span of, as I said, the span of all the gauge transformations, of all the actions of the gauge transformations. And then the kernel of my connection form, namely anything that it returns 0, it tells me, well, that was already in the horizontal space. There was no correction of frame necessary. That is the horizontal space setting. So it's defined by orthogonality with respect to this connection form. Now, here's the nice thing about it, is that you can talk about this connection form in the presence of boundaries. So the connection form, actually, we learned later, had already been found out by Singer and DeWitt, and DeWitt in his last papers talk about this. But they weren't really concerned with boundaries. But you can apply the same inner product and find, without restricting gauge transformations at the boundary, right? You're not fixing gauge or anything like that at the boundary. You can find what are the conditions for this decomposition to work also at the boundary. And you find field-dependent covariant boundary conditions. This is just to illustrate it. I'm not going to derive them here. And here, Si is the normal to the boundary. And it does give me a unique decomposition of any, if I input any field vector, it will give me a unique decomposition in terms of a horizontal part and a vertical part. This is just for pure gauge theory without matter. Here, this is just, as I said, the hash notation is just a notation for the infinitesimal vertical transformation. And these are the conditions on the horizontal field. I can just look at the horizontal field separately and see what conditions it has to satisfy. And it's divergenceless, and it's normal to the boundary. The psi, the gauge part of it, is unrestricted at the boundary. Okay, so finally, we can now, using all this apparatus, try to glue infinitesimal physical processes or perturbations. Again, here I'm talking about perturbations in infinitesimal physical processes because I'm generalizing to non-abelian theories. But let's not get too focused on that. So gluing to regional, horizontal, or physical fields. Let me now, I told you that H is, in the Helmholtz composition, this horizontal part would be the part that is not pure gauge, that is orthogonal to the pure gauge part. And now suppose I give you two of them. I give you one in sigma plus and one in sigma minus. And you can think of this as kind of saying, well, this is the state inside my ship, this is the state of the sea, whatever. So first of all, because of the boundary conditions that, the boundary equations that H satisfies, the difference between H minus and H plus at the boundary is itself a vector, a field space vector intrinsic to the field space of the boundary, and itself can suffer a decomposition like this in terms of physical engaged parts in the boundary. So the question that we're trying to answer is, can we glue arbitrary, again, if you think of H plus as the state inside the ship and H minus as the sea state, can we glue arbitrary states into one smooth universal horizontal field, H, or smooth universal physical field? And the answer is not always. So we can only do that if the boundary has no intrinsic degrees of freedom in a way. So in electromagnetism, it can contain charges and currents and so on. Right, but as long as the boundary does not contain those intrinsic degrees of freedom, then there exists psi plus minus, so a gauge transformation in this part and a gauge transformation in this part. So they belong to the group of gauge transformations of sigma minus and sigma plus, and these two gauge transformations will be functionals of the difference of horizontals in the boundary, so the difference of physical fields at the boundary, and they will be such that the gluing of the field, so these thetas are heaviside functions or characteristic functions of the two regions, so that H, big H, is itself a horizontal field. So I'm imagining the whole region has no boundaries. Notice that if I had gauge fixed, this would not exist, right? Because if I had gauge fixed in each region, as I said, there's no, or reduced, there's no more gauging these two horizontal fields up and down. So this process by which I allowed decomposition is what also allows me to match them. So what you find is that there is a closed formula for psi plus and psi minus. I'm not going to go into it. It's a bit overly complicated. You can look at the paper if you want. But there's closed formulas for how I'm going to adjust the two horizontal fields so that they match. So you could think of it, let's say in terms of the squadrons of the ships, you define some notion of a physical process here. Let's say it tells you, it gives you back what the center of mass is. You have another center of mass, and then it's giving you, if you put the two together, what the center of mass of the two systems would be. And so it would give you a dislocation of each one of the centers of mass. Of course, it's much more complicated in gauge theory, especially in non-abelian gauge theory, because you also need to take into account boundaries and so on. It's interesting that it really uses this Dirichlet-Neumann operator, which appears in other contexts of gauge theory, such as the BV formalism, when you're trying to talk about the gluing of Lagrangians with manifolds. So, in sum, when the fields are gluable, each region receives a malleable gauge readjustment, right? So that the universal joint field is now smooth and what we have called purely physical. And finally, we get to the question that we started with is, well, how unique is this gluing? If the regional physical information determines psi plus and psi minus, this readjustment, only up to some psi tilde plus minus, there could be more than one global physical field that differs from the first one only by parochial regional symmetries, right? Because I'm imagining I'm twisting this up and down like this, but I'm asking if this twisting is not unique, there might be two physically different universal fields that corresponds to two different twists. And if this ambiguity exists and is rigid, we'll have shown the top main claim is that for certain regional gauge invariant data, which can be glued together, there remains a residual variety of universal gauge invariant data obtained from this gluing. And this variety is going to be parametrized by regional rigid transformations, not rigid malleable transformations. So the way that you get to that is that there's a way of plucking out the rigid symmetries from the malleable ones. And the truth is that I lied to you before. The field space phi is not, in fact, a principal fiber bundle. The quotient space is what's called a stratified manifold. And that's just because there exist certain field values which are reducible. So for certain of the field values, you have transformations that don't change them. So this is like in Minkowski, right? You have killing symmetries. The killing symmetries really don't change Minkowski. So you have transformations, translations, and so on that don't change the metric at all. And these are a generalized version of that for Young Mills. It's reducible. Of course, not all field configurations admit that. Only some field configurations will admit this generalized version of killing. And moreover, these what we call stabilizers, the killing, they're always finite. So this is a way that you pluck out the rigid symmetries from the malleable ones. They come out only in the case where the field configuration has stabilizers. And these stabilizers, let's call them psi tilde to match what we had before. And thus we find the ambiguity. There's an ambiguity in the reconstruction up to regional rigid symmetries, psi tilde. And the reconstruction of the global H from the regional little h's, H plus and H minus, leads to different H plus and H minus for H tilde plus different from H tilde minus, only in the presence of matter, psi. There can't be any matter at the intersection, as I said before, for the gluing, and this is also, if there were, here you see that you wouldn't be able to use these different regional symmetries anyways. But you can see here, this is psi hash, and now if I include matter, I don't have just this term for the gauge transformations in field space, I also have some other term here. I'm imagining it acts in the fundamental representation on the matter fields. So a different choice of psi tilde would not act on the gauge field, but it would act on the matter field, and I would get this regional configurations which are different by an action of a rigid gauge symmetry on each region. And then when this happens, there's this variety is related to conserved charges associated to the rigid symmetries, and so on. And there's a lot more to say here, but I think I'll stop here. Thank you.
Okay.
Thank you. A general comment and a specific comment. The general comment is that I'm delighted, in a sense, because I've been writing and screaming and preaching gauges and not mathematical redundancies for here. I felt myself San John in the desert, nobody paying attention. Finally, was paying attention. So I couldn't agree more. And the way Jeremy put it in the beginning, it's what I tried to write in these old papers for long. However, Jeremy being Jeremy, it now sounds extremely clear and clean in respect of what I was trying to do before. And I like to see this mathematical elaboration of that. That's a general comment. The specific comment is that you are focusing here on subsystems as space-time regions, and the boundary between systems as boundary between space-time regions. This is seems to be very useful, especially in the gauge theories, to understand what happened, and also to understand a lot of the mathematics which is happening now in theoretical physics in various pieces of the discussion. However, the notion of subsystem is more general when you with respect to this gauge taking sense as relational. Gauge is the reason we use gauge is because physical variables are relationals between our regular world and subsystem. That's the deep message of gauge theory. But it's not just in physical subsystem. And the simplest example, which is in front of our eyes, has been in front of our eyes for a long time, is just the classical field theory behind QED, electromagnetism. If you take the electromagnetic field, the gauge invariant things are just the electric field and the magnetic field, period. So why can't we couple it to a Dirac field? We cannot. Right? There's no coupling between E and B and the Dirac field. The reason is because in the field theory of electromagnetism plus the Dirac field, the coupling between the two is gauge invariant, that is a coupling between a gauge variant part variable of the magnetic field and a gauge variant part of the Dirac field. So if you separate, if you cut the two, and here the cut is not a cut in space-time, it's a cut between two different components of the universe, sort of photons and electrons. If you think that gauge is mathematical redundancy, you don't understand how it's possible to couple the two, because the gauge invariant part of the photons don't couple to the gauge invariant part of the gauge coupling is gauge invariant. The coupling is gauge invariant, but it's a coupling because a non-gauge invariant variable one, the non-gauge invariant part couple there. So the non-gauge, this is an exact analog of this boundary variables that you are taking out here, but it's not just on field on space-time boundaries. It's more general to boundary to components of the universe.
Right, so I mean, I totally agree with you. Even if you want to write an action for anything, for any gauge theory, you need to use the gauge variant variables, in fact. Right? So it's very general that you need to use it for practical purposes and also for these more conceptual reasons. What I find interesting in terms of relational concepts is this fact that you only notice this this possibility when you have it's a relational concept in itself, because you only notice it when the gauge field is slipping with respect to the matter field, in a way. So it's only when you have the matter field as well that you find this concept here. So I think that's a very nice instantiation of this concept. Jeremy, do you want to come over here?
I totally agree with Carlo. I'm grateful for the gracious comment. I agree with what you said.
Hello. Michael Duff, Imperial College. 40 years ago, I wrote a paper with Steve Christensen on the Unruh effect, which provides an example of what you're talking about. The spin connection for a uniform gravitational field is non-zero, but it is pure gauge. The curvature vanishes. But as the Unruh effect illustrates, there's a physically measurable.
That's very interesting. Yeah, we were actually thinking about Unruh effect a while ago, but I'll have a look at your paper and get back to you.
Hello. Thank you for the presentation, and I'm happy that you promote this topic of direct empirical status, because I was saying to Jeremy that I have written a PhD dissertation on this just a couple of months ago. So I have the following question. Firstly, what do you say about action at a distance theories and interpretations, where there is no matching between the boundary region and the complement of the boundary region? Because in action at a distance theories, you may have just something going in some domain, then you have an identity transformation around it, and then you have something going on very well beyond that the boundary region. So there will not be this kind of matching condition in this case. And secondly, I'm just, I don't know if this is a question for you or for Carlo already, but I'm a bit confused about how you use his Y-gauge article to motivate the non-gauge fixing. Because I would say that his approach is about horizontal transformations. So it is horizontal transformations which would ensure the matching. But gauge fixing occurs in the fibers, so it's vertical.
So I'll answer the second part at least. So I think what in the article by Carlo, what you're imagining, as I mentioned, is an actual reduction. You're going to the gauge invariant variables themselves, and a gauge fixed formulation is gauge invariant as well. And so what he's advocating is to keep some flexibility if you need to couple systems. And the flexibility, as I have described it here, is the possibility to have some notion of what is physical, which is the horizontal part, but still keep the flexibility of moving this up and down, so that you can match different notions of what is physical. And the first question was about the action at a distance. I haven't really thought about that, so I don't know if you have.
Yes, I would only add to what Enrique said. Thank you for the questions. I would only add that about the first part, it's true that everything we've done has in fact been, that Enrique and collaborators have done has been in field theory, and therefore with this space or space-time boundary, and hence the word gluing is very natural. But I would hope that the morals would apply where it's subsystems rather than regions, and it's certainly true that much of that framework discussion of my first third of the talk was there was nothing about the dynamics really. It was just about physical state, mathematical state, symmetry, system, subsystem. So action at a distance versus continuous action dynamics shouldn't make a difference to that broad story. After all, Galileo's ship, there's no issue about whether it's contact or non-contact action in the dynamics.
Hello. May I ask a relatively radical question? Radical in the sense, could these principles in this symmetry be applied on black holes, and more specifically on their boundaries, for example, the event horizon? Because in that case, you might treat the black hole like some kind of subsystem of the universe or so, and then connect it to one another and say, well, in certain ways it's asymmetrical, but it does have some symmetry. I don't know quite much about gauge theory yet, so. But imagine one would use that and combine it with Jared's insights about the Schwarzschild radius and that other component. No. Oh, do you want to comment on that? Or do I have to?
I can make just a small comment here. In the loop quantum gravity calculation of the Hopfmuller entropy, what is computed is exactly the kind of boundary variables that would be gauge invariant, gauge non-invariant if you cap there, which lives on the horizon. So there is a direct relation between what Henrique is describing in general and the physics of the black hole entropy as viewed in this framework of quantum gravity.
I don't have much time. Aldo has thought a little bit more about this. We haven't yet tried to apply it, but he has mentioned it and cited these works in quantum gravity as an inspiration. So.
Is it a finger on this? Yeah.
Well, just briefly, there's something very interesting happening at the horizon of a black hole in connection with gauge transformations. Because in black holes, or general coordinate transformations are also gauge transformations. And you find that at the horizon, you have to make a shift. You have to readjust space, time, and fast particles go by. And that shift is a gauge transformation. It's a general relativistic gauge transformation. So the gauge transformation of generators of the theory, which in the bulk are unobservable, basically because of gauge invariance, at the horizon generate degrees of freedom. The conjecture is the same happens to the other local symmetries. So the other local symmetries, such as the electroweak transformation or color, they The generators of that symmetry are gauge generators in the bulk, therefore locally unobservable, but there are degrees of freedom on the horizon, where whenever you attach part of the inside of the black hole or the other side of the black hole onto this side of the black hole, then you have to associate that by a Euler transformation and by a gauge transformation. So the question was well put, and there are interesting possible answers. Although I must immediately confess there are many mysteries there that I also don't understand.
So I think this formalism would be very interesting to apply to this case, because I think this is exactly this type of gauge transformations at the boundary between two subsystems is precisely what the formalism is engineered to describe and to attack. We haven't yet done the full work for gravity, for spin 2 in general, but it shouldn't be that.
Gravity is also gauge.
Of course, no, of course. No, I completely agree. It just hasn't been done for that.
Okay, thanks. So I want to start by saying that I'm really happy with the general thrust of this. But there seems to be something that is kind of missing for me in the talk and some of the discussions, which is the extent to which the empirical implications are due to genuine symmetries or just kind of approximate symmetries. So, take the Galilean ship, right? If you are in the ship and you don't see the shore, then there is no real empirical consequence. If you open the window and you can see the shore moving, then photons are hitting your eyes, and you can, and those images of the shore are the empirical consequences. But those are non-trivial interactions between the shore and the ship that are not symmetries. They're things that I'm seeing in my eyes. Now, of course, those interactions are very small compared to the momentum scales of the shore. But it seems to me that the formalism that you're using is super useful, but there's, I wonder if it can handle this kind of, or what you have to say about at least this idealization.
So I'll say something, I'm sure Jeremy wants to say something as well. There is a component that I mentioned briefly, that you only have the empirically significant symmetries in this sense if there is no matter content in between the two systems. So I think Greaves and Wallace, they mention a similar condition which they talk about as isolation of the two subsystems. There's some degree of isolation between the two subsystems. And this may be only approximate. I think in the cases that you're describing, there might be some small violation of this.
It has to be approximate. If there was a complete decoupling between these systems, then there would be no way to tell whether or not the ship is moving or not. And so, what is the empirical consequence there? So what I'm saying is that...
Well, right, so we're using empirical... so what I would say is that all we are saying in this context is that there are... Maybe we're using empirical in a different mathematical sense. We're saying there are different gauge equivalent universal configurations whose restrictions match, which are regionally indistinguishable but are globally distinguishable. So there's some relational difference between the two. And of course, what I also haven't talked about is we can accommodate non-trivial topology to this, and that adds some other things.
Well, this may or may not appease you, dear Sean, but while I agree with what Henrique said, I would just add in, again, a general kind of way. We did always admit, both for the gauge situation and the Galileo's ship, that there is this extra information in the relation, and of course inspired by Carlo's fleets of spaceships. And you're commenting on, roughly speaking, how we've all just put it in one box and labelled it relational gluing info, and you're rightly stressing that there's cases and cases, and it can be arcane quantities for which the difference in the values in the two scenarios considered is very small, and that's where we
the kind of situation that would apply to, it is approximately isolated. I need a very special thing, like Wallace makes the joke about if Galileo had a GPS device down there in the cabin, as well as fish and butterflies, he would be well able to know whether he's moving. So I agree, there's a kind of conceptual, perhaps one can make something precise in a formalism about it, but certainly there's a conceptual concession to be made that what quantities count as salient, to use the word of my very first slide, is a matter of judgment and practice and varies from case to case. And we certainly didn't do that. We simply said, typically one thinks it's the very same physical state of affairs if all the quantities get the same value, because we tend to think that states and quantities separate one another. And so it's a salient set only, and it's a matter of judgment and practice, case to case varying what counts as salient.
That's the trouble with this. We shouldn't really have to be an athlete to be honest.
One last question.
On trivial homotopy class is not a simple example. I mean, if you have a system that you gauge transform, and if you gauge transform everything, including the infinity, there is full equivalence. But of course, if you omit the gauge transformation at infinity, by making a cut somewhere, the two are no longer equivalent. And of course, you cannot deform them into each other continuously if they belong to non-trivial homotopy classes. So I would guess that's a very simple example where two local gauge transformations that are not accompanied by the appropriate transformations at infinity will lead to possible observables that are different. Is that not a simple, very simple setting of this type?
So, what I would say here is that in these finite cases, we have not restricted gauge transformations at the boundary. We have, because what you're describing is true, and
you know, if you say my boundary is my reference system, your
yeah.
pose that is not moving, and if you take just a transformation of everything except for your reference system, this is exactly your shift, and then you ask yourself under what circumstances did you find in your local systems differences. These are simple examples for it, because locally the gauge transform systems, if you're not transforming the boundary with it, are not equivalent.
Sure. I agree. So if you want to look at the asymptotic case, I'll pass it on very shortly. Aldo has a solo authored paper in which he describes how you would recover our rigid symmetries and more, in fact. So he talks about asymptotic infinity and how you recover super translations and so on as well from this perspective. Yeah, I think that the interesting thing about this is that you can treat at first boundaries as being completely fiducial. So you're right, you could fix everything at the boundary, but there are other issues that come about when you try to do that. And this is the standard approach, which has some drawbacks. I mean, we can talk about it later, but in previous talks, that's how I introduced the topic about what would happen if you gauge fix at the boundary. But I think that would go into a long tangent here, so we can leave it for discussion.
I'd only add that I think Nicholas Tay looked at the asymptotic infinity aspects of the Greaves-Wallace proposal. So there is some pickup in the philosophy literature about your comment, if I may say.
Before thanking the speakers again, just to say the afternoon program is unchanged. We reconvene at 1:30 after lunch.